Hello and good morning to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we'll learn about a very important concept in operating system that is referred to as a thread. Now, a thread in an operating system is a flow of execution through the process code, wherein each flow maintains its own program counter, system registers, and a stack in order to keep track of the status of execution or state of execution. Now, here it is to be understood that a process can have in it one or more than one such flows. This implies a process can have in it one or more than one threads. Now, let us try to understand some of the important attributes that threads belonging to a process shares within them. Threads belonging to a process shares information like code segment, data segment, and open files that are associated with the process. Again, I'll repeat it. Threads belonging to a process share among them code segment, data segment, and open files that are associated with the process. This also implies that if any change is brought about to either code or to the data or to the open files that are associated with the process by any of the threads or by any of the thread, necessary changes will be reflected to all the other threads belonging to a process. From here, we can understand that all the threads belonging to a process share the same memory. Now, why it's important to use threads? So, threads provide a way to improve the overall application's performance through parallelism. What does it imply is multiple threads belonging to a process can be made to simultaneously perform operation in order to enhance the overall throughput of the process. So threads provide a way to improve the overall application's performance by enforcing on parallelism. Now, it is also to be understood that threads represent a software approach to improving the overall performance of the operating system. So it is done through software packages, or it is implemented through software packages with the motive of improving the overall performance of the operating system. So it is a software approach to improving the overall performance of the operating system. Threads provide a suitable foundation for parallel execution of applications on shared memory and multiple processors. So we will understand this in a greater detail in subsequent slides. But here for now, we need to understand that multiple threads belonging to a process may be placed onto different processors in a multiprocessor architecture in order to enhance the performance or in order to reduce the overall execution time. So threads provide a suitable foundation for parallel execution of applications on shared memory and multiple processors. Now let us try to differentiate between the traditional process execution and execution of process using threads. So in traditional approach, we have a process P with which we have a set of data structures associated. So these are system registers, counters, program counter, and stack to keep track of the status information of the execution of that particular process. So associated with every process, we have system registers, we have program counter, and we have stack to keep track of the status of execution or state of execution. And process has its own data and files with associated code. So process using the code, making use of data and files, perform operation where the operation is kept track with the help of the various data structures like system registers, counters, and stack. So this is the way how process used to traditionally get executed. So every time a process executes, the process has to be loaded onto the main memory, and it has to be provided to the central processing unit for performing operation. So every time a process is to be executed, it has to be brought onto the main memory, and then the execution has to be done by CPU. So every time a process is to be executed, memory allocation is to be done in the main memory. Now, multiple execution of such processes or multiple execution of P would require multiple memory allocation to be done in the main memory. Now, this is very resource intensive or very heavy on the utilization of resources. So whenever multiple instances of the process is to be executed, multiple times the process has to be loaded onto the main memory and it has to be executed by the CPU. So it's very resource intensive, or it non-optimally utilizes memory, the computational resources. So in order to overcome that, they thought of a concept called as threads, where multiple threads belonging to the same process resides at the same memory allocated to the process. So this is the way how the orientation of process P will be done with the help of threads. So here what we have is we have in the individual threads maintaining their own data structure to keep track of the state of execution. So each and every threads they have their own system register, they have their own program counter, and they have their own stack in order to keep track of the status of execution, wherein the different threads that are there belonging to a process share the same code, data and files. So all the threads belonging to a process share the same code, data and files, but they maintain their own local data structure in order to keep track of the state of execution. So here, since they share the same code, data and file, so it is understood that all the threads belonging to a process share the same memory belonging to the process in the main memory. So here threads are lightweight or less resource intensive. So every time I need to perform an operation pertaining to a process P, I need not load that particular process onto the main memory. So what I can do is I can activate different threads belonging to that particular process in order to perform operation. So since all the threads belonging to a process utilize the same memory space, so these are less resource intensive compared to that of the traditional way how the processes are being executed or processes are being handled. So this is one of the major advantage of using threads over the traditional approach of process execution. So here threads T1, T2, T3 belonging to process P share the same code, they share the same data and they share the same files, but they maintain their own local data structure in order to keep track of the state of execution, and all the threads belonging to the process they reside on the same memory. So frequent loading of the process onto the main memory is not required. Now let us try to differentiate between a process and a thread. Now, to begin with, a process as understood is heavyweight or resource intensive. So every time an instance of a process is to be executed, it is to be brought onto the main memory and the execution is to be done. So every time a process is loaded onto the main memory, separate memory allocation is to be done to that particular instance. So it's very heavyweight or resource intensive. Now in case of process, switching happens through operating system. So switching basically refers to transition from one process to another process. So here, in case of process, switching happens through the operating system. Now, the next important point you need to understand is that every process executes in its own memory, utilizing its own resources, that is data and files. So every process executes in its own memory, utilizing its own code, data and files. So this is what we have understood. So every time an instance of a process is to be executed, it executes at its own memory, utilizing its own code and file resources. So this is very resource intensive or very heavyweight. Now, when a process is blocked, then no other process can execute until unless the blocked process is unblocked. Now this is the way how the orientation of process execution is done. So whenever a process is blocked, then no other process can be executed until unless the former process that is blocked is not unblocked. Now, multiple processors without using threads utilizes more resources. So this we have already learned. So multiple processors without using thread uses more resources because every time a process instance of the process is to be executed, it's to be loaded onto the main memory. That will take considerable amount of memory space. Now, in multiple processes, each process operates independently of the other. So this is also understood. So in case of multiple processes, the processes operate independently of each other. Whereas in contrast, we have understood in case of threads, the threads belonging to a process share the common memory, and if any change is brought about to any of the attributes of the process, then the necessary changes are reflected to all the threads belonging to that particular process. So this in brief is the description of a process. So process is rather heavyweight or resource intensive. Context switching happens through the operating system. The process executes in its own space, utilizing its own code and the file resources. When a process is blocked, then no other process can be executed until unless the blocked process is unblocked. And multiple processes without using threads definitely utilizes more memory space, more resources. So in multiple processes, each process operates independently of the other process. Now let us consider threads. So threads are lightweight or less resource intensive because we've understood that different threads belonging to a process, they share the common space. They share where they share code, they share data, and they share the open files that are associated with the process. Now since a thread, threads belongs to a process, right? So context switching does not happen through the operating system. So since thread is a intra-process affair, so context switching does not happen through the operating system. Now, threads belonging to a process share the same code, they share the same open files, they share the same data with all the other threads belonging to a process. Now, likewise, while one thread is blocked and waiting, a second thread in the same task can perform its desired operation. So this is one of the important attributes of the thread. So we'll come to it in a greater detail in the subsequent slide. So what we can have is threads belonging to a process deployed onto different processors in a multiprocessor architecture, and even if one of the threads that's deployed onto one of the processor is blocked, all the other threads deployed onto the other processes can perform its desired operation. So that is the intention of this particular point. So here, while one thread is blocked and waiting, a second thread in the same task can perform desired operation that's deployed in some other processor in a multiprocessor architecture. Now, multi-threaded process definitely uses fewer resources because different threads belonging to a process, they share the same resource or memory space. And one thread can read, write, or change another thread's data. So as we have learned that threads belonging to a process, they share the common space. So if any change is brought about to either code or to the data or to the open files that are associated with the process, the necessary changes are reflected to all the other threads belonging to that particular process. So these are some of the major distinctions between a process and a thread. Now let us go through some of the advantages of threads. So threads, as understood, it minimizes context switching time. Threads provide concurrency with an objective of enhancing the overall system's performance and responsiveness. Threads facilitate efficient communication. It is more economical to create and maintain threads. And threads allow utilization of multiprocessor architecture to greater scale and efficiency. wherein different threads may be deployed onto different processors belonging to a multiprocessor architecture. So these are some of the notable advantages of threads. So threads, they minimize context switching time, it provides concurrency, it facilitates efficient communication, it is more economical to create and maintain threads, and threads can be deployed over multiprocessor architecture to a greater scale and to enhance efficiency, wherein different threads perform operation on different processor in the multiprocessor architecture. Now let us try to understand different types of threads. So there are two different types of threads. So threads are implemented in following two ways. The first one is called as user level thread, and the second one is called as kernel level thread. So user level thread, as the name says, these are threads that are created and managed by the user in the user space. So user level threads are threads that are created and managed by the user in the user space. So these are called as user managed threads. Now, how are user managed threads created and managed? So user level threads are threads that are created with the help of software packages. So for example, we have package for creating P threads. So user level threads are threads that are created with the help of software packages, which contains code for creating threads, destroying threads, enabling threads to communicate with each other, scheduling execution of the threads, and saving and restoring the threads content. So there are thread packages that allows you to do this. So user level threads are user managed threads, which imply threads that are created by user and managed by the user in the user space. So this is done through thread libraries, which have code for creation of the thread, destruction of the thread, enabling threads to communicate with each other, scheduling execution, and saving and restoring threads content. Now let us go through some of the advantages of user level threads. So in case of user level threads, so here just see I have a very simple schematic representation where you have multiple user level threads T1, T2, T3 belonging to a process P that's created and managed in the user space. So now let us go through the advantages and disadvantages of user level threads. So let us first discuss the advantages. So the first advantage is that switching does not require kernel mode privileges. So this is one of the major advantage of user level thread. So it does not require kernel mode privileges. So it can run on any operating system. So this is the second important advantage of user level thread. So it can run on any operating system. Now scheduling can be application specific depending upon the requirement of the application. So since it does not require any kernel mode privileges, so it is faster to create and easy to manage. So user level threads, they do not require any kernel mode privileges. It can run on any operating system. Scheduling can be application specific or based on the demand of the application, and these are fast to create and easy to manage. Now let us discuss disadvantage of user level thread. So one of the major disadvantages of user level thread is if one of the thread A is blocked, then all the other threads belonging to that particular process will be blocked. For an example here in this schematic representation, if a thread T2 makes a blocking system call, it wants to make use of certain IO device that is not available as at the current point in time. So T2 is blocked because T2 has made request for a resource that is not available, so T2 is blocked. So since T2 is blocked, then T1 and T3 belonging to process P will also be blocked. So here this is to be understood that if one thread in a process is blocked, then all the other threads belonging to that particular process will be blocked. Now here it is to be understood that although we have multiple threads T1, T2, T3 belonging to process P, the overall execution of the threads belonging to a process is completely dictated by the scheduling algorithm that is deployed by the operating system, right? So it is to be understood that the execution of the threads belonging to a process is completely coordinated by the operating system's scheduling algorithm. And here, coordination between different threads happen through coordination variables like semaphore and mutex. So it is to be understood that um, we can create multiple threads belonging to a process, but the overall execution of the threads is coordinated by the operating system scheduling algorithm and controlled with the help of coordination variables like semaphores and mutual exclusion mutex. So we'll come to that, but for now just remember that in case of user label thread, if one of the thread is blocked, then all the other threads belonging to that particular process will be blocked. Now let us move on to so some of the examples here. So examples of POSIX-P threads, Windows 32 threads, Java threads. So these are examples of user level threads. So now let us move on to kernel level threads. So kernel level threads are threads that are created and managed by the operating system kernel in the kernel space. In contrast to user level threads that are created and managed by the user in the user space, kernel level threads are created and managed by operating system kernel in the kernel space. So operating system kernel supported and managed threads. Now the kernel maintains context information for the process as a whole and for individual threads belonging to the process. Now scheduling is done on thread basis. So kernel level threads are maintained by the kernel, where the status information of the threads are also maintained by the kernel. Now the kernel performs thread creation, it performs scheduling, and it performs management in the kernel space. So this is what we have learned. So it performs thread creation, scheduling, and management in the kernel space. Now kernel threads are generally slower to create and manage than the user threads. And it is also to be understood that we can have only restricted number of kernel threads because resource is very constrained, or it has to be optimally utilized in context to kernel. So we have a restricted number of kernel threads. So kernel threads are generally slower to create and manage than compared to that of a user thread. Now kernel thread requires kernel mode switching. In case of kernel threads require kernel mode privileges. So this is to be understood. So here what we have understood is that kernel level threads are threads that are created by the operating system kernel and managed by the operating system kernel in the kernel space, wherein the operating system kernel maintains the context information of the process as well as it maintains the context information of the process, and scheduling is done on thread basis. So here kernel performs thread creation, scheduling, and management. And we have also learned that kernel threads are generally slower to create and difficult to manage compared to that of user level threads. And context switching in case of kernel thread requires kernel mode privileges or happens to the operating system kernel. Now let us go through some of the advantages of kernel level threads. So what we can have is we can have multiple kernel level threads deployed over multiple processors in a multiprocessor architecture performing desired operations. So if any one of the kernel level thread is blocked, then other kernel level threads belonging to a process deployed onto the multiprocessor architecture may perform its desired behavior. So in contrast to the user level thread, wherein if one of the thread is blocked, then all the other threads belonging to the process is blocked. Here that may not happen because different kernel level threads may be deployed onto different processors in the multiprocessor architecture. So even if one kernel level thread is blocked, then other kernel level threads belonging to the process may perform operation. So it can simultaneously schedule multiple threads from the same process onto the multiple processes that are there in the multiprocessor architecture. So even if one thread belonging to a process is blocked, the kernel can schedule another thread of the same process onto different processor and perform desired operations. So this is one of the major advantage of kernel level thread over user level thread. So kernel routine themselves can be multi-threaded. So this is one of the major advantage of kernel level thread over user level thread. As we have learned, kernel level thread can be of limited numbers, but different kernel level threads belonging to the same process may be deployed onto the multiple processes in the multiple processor architecture and make it perform operation. So this is the distinction. These are some of the important distinction between user level thread and kernel level thread, and the advantage that kernel level thread has over user level thread. So some of the examples of kernel level threads are Windows XP 2000, Solaris, Linux, 265 Unix, Macintosh OS. So they basically implement kernel level threads. Now let us move on to a simple distinction between user level thread and kernel level thread. So user level threads, as understood, these are faster and easy to manage. Kernel level threads are slower to create and difficult to manage. In case of user level thread, implementation is done with the help of thread libraries. In case of kernel level thread, implementation is done by the operating system. User level threads are generic and can be used in any of the operating system, whereas kernel level threads are kernel specific and it can be used only on a specific operating system. Now, multi-threaded application cannot take advantage of multiprocessing, whereas kernel routine themselves can be multi-threaded. So this is one of the major distinctions we have learned. So in case of user level threads, if one of the processes is blocked, then all the other processes belonging to that particular thread is blocked. And in case of kernel level thread, even if one of the thread is blocked, then all the other threads belonging to the same process deployed over multiprocessor architecture can perform desired operation. So multi-threaded application cannot take advantage of multiprocessing, whereas kernel routine themselves can be multi-threaded. So these are some of the basic distinctions between user level threads and kernel level threads. Now let us move on to multi-threading models. So now why do we need multi-threading models? So as we've understood that if a process belonging to if a thread belonging to a process is blocked, then all the other process belonging to that particular process, all the threads belonging to that particular process is blocked. So this is one of the important characteristics of user level threads. So if a thread belonging to a process is blocked, then all the other threads belonging to that particular process will also be blocked. So in order to overcome this problem associated with user level threads, what we can do is we can map multiple user level threads onto multiple kernel level threads, deploy the kernel level threads onto the multiprocessor architecture, and then if any of the thread is blocked, then the different kernel level threads that are mapped onto different multiprocessor architecture can perform operation. So in situation, if a thread is blocked, then what we can have is we can have other threads that are that may be used in order to perform operation. So multi-threading model basically refers to a mechanism of mapping user level thread onto the kernel level threads, just to ensure that operation carries on, or performance of execution carries on. So for now, just remember that multi-threading model is a model that is used in order to map user level thread onto the kernel level threads. And we will try to understand what are different types of multi-threading models that can be potentially pursued. So some of the operating system provides the facility to combine user level threads and kernel level threads. In a combined system, multiple threads within the same application can run on multiple processors parallelly, and a blocking system call need not block the entire process. So this is what we have learned. Yeah, this is what we have understood. So in a combined system, multiple threads within the same application can run parallelly on multiple processors, and the blocking system call may not or need not block the entire process. So here what we can have is we can have multiple user level threads being mapped to multiple kernel level threads, and these mapping may be deployed onto multiple processors in the multiprocessor architecture. And in such situation, even if one of the thread is blocked, then only the associated kernel level thread will be blocked, that is deployed onto a specific processor in the multiprocessor architecture. So all the other mappings can perform execution in parallel. So this will basically help us in continuing the execution. So this is the advantage of multi-threading model. So multi-threading model allows us to combine user level thread with the kernel level thread and deploy that combination over multiple processors in the multiprocessor architecture. So in such situation, if any thread makes a blocking system call, then it will not have an influence on the other combinations that are deployed onto the other processors in the multiprocessor architecture. So this ensures continuation of execution even when a portion of the required processing is blocked, or a selected number of threads are blocked. So now let us try to understand some of the multi-threading models that are there. So there are basically three types of multi-threading models. So first one is called as many-to-many. Second one is called as many-to-one, and third one is called as one-to-one. So in many-to-many, multiple user level threads are mapped onto multiple kernel level threads, with the imposition that the number of kernel level thread should be less than or equals to the number of user level threads. So that is the constraint imposed on many-to-many relationship. So in case of many-to-many relationship, you have multiple user level threads mapped onto multiple kernel level threads, with an imposition that the number of kernel level threads should be less than or equal to the number of user level threads. So that is an imposition. So in case of many-to-many model, many user level threads are mapped onto many kernel level threads, with an imposition that the number of kernel level threads should be less than or equals to number of user level threads. Now in case of many-to-one model, in contrast to many-to-many model, in case of many-to-one model, many user level threads are mapped onto onto one kernel level thread. So again I'll repeat it. In case of many-to-one relationship, many user level threads are mapped onto a single kernel level thread. Now in case of one-to-one relationship, one user level thread is mapped with one kernel level thread. Again I'll repeat it. So one user level thread is mapped to one kernel level thread. So in case of many-to-many relationship, many user level thread to many kernel level thread, with an imposition that the number of kernel level thread is less than or equals to the number of user level thread. In case of many-to-one relationship, many user level threads are mapped onto a single kernel level thread. And in case of one-to-one relationship, one user level thread is mapped onto one kernel level thread. So here what we have learned about is, we have learned about the concept of multi-threading, wherein user level threads are mapped onto kernel level threads, just to ensure that the execution continues even if some of the threads are blocked. Now let us try to understand the multi-threading models in greater detail. Now let us start with the simplest of the multi-threading model, that is many-to-one. Now in case of many-to-one, as understood, many user level threads are mapped onto a single kernel level thread. So here many user level threads are mapped onto a single kernel level thread. Now this particular structure has a typical problem in it. Now just see, if any process belonging, any thread belonging to a process makes a blocking system call, then the kernel level thread will also be blocked. Since there are other threads belonging to the process that is associated with the same kernel level thread, so all the other threads belonging to the process will also be blocked. Okay, so here you see it is to be understood in many to one model, since multiple user level threads are mapped onto a single kernel level thread. So if a thread makes a blocking system call, then the kernel level thread will also be blocked. Subsequently, all the other threads that are associated with that kernel level thread will also be blocked. So if a thread in case of many to one model makes a blocking system call, then all the other threads belonging to that particular process will also be blocked. So this is one of the major lag of many to one model. So since in case of many to one model, multiple user level threads are mapped onto a single kernel level thread. So if a user level thread makes a blocking system call, then the kernel level thread will be blocked. Subsequently, all the other threads belonging to that particular process will also be blocked. So here that is one of the major lag of many to one model. So in case of many to one model, many user level threads are mapped onto single kernel level thread. So here thread management is done in the user space by the thread library, and in case in the kernel level thread is managed in the kernel level by the operating system kernel. Now when a thread makes a blocking system call, then the entire process will be blocked. So this is what we have learned. So if a thread makes a blocking system call, then the kernel level thread will also be blocked. Subsequently, all the other threads associated with that kernel level thread will also be blocked. So the entire process will be blocked in case of many to one model if a thread makes a blocking system call. So only one thread can access the kernel at a time. So multi-threads are unable to run in parallel on multiprocessors. So irrespective of whether you have a uniprocessor architecture or multiprocessor architecture, since one kernel level thread can be deployed onto only one processor, so such kind of orientation or many to one model cannot make use of multiprocessor architecture, because one kernel level thread can be deployed onto only one processor. So irrespective of having multiple user level threads, you can deploy such architecture only onto a uniprocessor system. So only one thread can can access the kernel at a time. So multiple threads are unable to run in parallel on multiprocessor systems. Since the kernel level thread can be deployed onto only one processor, so even if you have multiple user level threads, so they cannot run on parallel, or they cannot run parallel, so or they cannot make or take advantage of multiprocessor architecture. So these are some of the important characteristics of many to one model. So here in case of many to one model, it is to be understood that multiple user level threads are mapped onto a single kernel level thread. So if any of the thread makes a blocking system call, then the kernel level thread will be blocked. Subsequently, all the other user level threads that are associated with the kernel level thread will be blocked. So here it is understood that if a thread makes a blocking system call, then the entire process will be blocked. Now, as schematically represented, in case of many to one model, since multiple user level threads are mapped onto a single kernel level thread, and the single kernel level thread can be deployed onto only one processor, irrespective of whether you have a uniprocessor or multiprocessor architecture. So it can be deployed on only one processor, so it cannot perform parallel execution over multiple processors in the multiprocessor architecture. So this is one of the major lag of many to one model. So if the user level thread libraries are implemented in the operating system in such a way that system does not support them, then kernel level thread uses the many to one model or many to one relationship. So examples, you have Solaris green threads, so you have GNU portable threads. So some of the examples of many to one multi-threading model. So this is a very important orientation of user level thread and kernel level threads one needs to understand. Now let us move on to the second model, that's called as one-to-one model. Now, in contrast to many-to-one model, here what we have is we have one kernel level thread over or for every user level thread. So here there is one-to-one mapping between user level thread and kernel level thread. Now, this orientation overcomes the lag of the many-to-one model. The first lag of many-to-one model was, in case of many-to-one model, multiple user level threads are mapped onto single user level thread. So if a user level thread makes a blocking system call, then the kernel level thread will also be blocked, and subsequently all the other threads belonging to that particular process will be blocked, or related to the kernel level thread will be blocked. So one-to-one model tries to overcome the first lag of many-to-one model by mapping one user level thread to only one kernel level thread. So even if a user level thread issues a blocking system call, then a particular kernel level thread will be blocked that is related to only that user level thread. So other kernel level threads will not be influenced in case of one-to-one model, in contrast to many-to-one model. So this is the way how one-to-one model overcomes the lag of many-to-one model, the first lag of many-to-one model. So in case of one-to-one model, since one user level thread is mapped onto one kernel level thread, so even if a user level thread makes a blocking system call, then only the associated kernel level thread will be blocked, with no influence on the other kernel level threads which are mapped to other user level threads. So this is the way how one-to-one model tries to overcome the lag of the many-to-one model. So as understood, one user level thread is mapped onto one kernel level thread. So if a user level thread issues a blocking system call, then only that particular kernel level thread will be blocked, where it will not have influence on the other kernel level threads. Now, the second lag of user level, the many-to-one model was, many-to-one model was not capable of utilizing the capabilities of multiprocessor architecture, because one kernel level thread can be deployed onto only one processor in the system, irrespective whether the system has a uniprocessor architecture or a multiprocessor architecture. So we have understood that many-to-one model cannot fully utilize the capabilities of multiprocessor architecture. But here, in contrast to many-to-one model, in case of one-to-one model, we have multiple kernel threads created for user level threads. So we can deploy the kernel level threads onto the specific processors in the multiprocessor architecture and make full use of the capability of the multiprocessor architecture. So this is one of the major advantage of one-to-one model. So different kernel level threads can be deployed onto different processors in the multiprocessor architecture and can be made to perform operations in parallel. So this is one of the major advantage of a one-to-one model. So in case of one-to-one model, we have specific kernel level threads for specific user level threads, and these mappings can be placed onto specific processors in the multiprocessor architecture and can be made to perform operation. So this is the major advantage of a one-to-one model over many-to-one model. But a one-to-one model has a limitation as well. We can have only restricted number of kernel level threads that are managed in the kernel space, because we need to make optimal utilization of memory space. So we can have only restricted number of kernel level threads, but over that it has many advantage over over many-to-one model. So here, in case of one-to-one model, Let us go through the description. So each user label thread is mapped to a kernel label thread. So it provides more concurrency than many-to-one model. So this is what we have learned. So we can have different combinations being deployed onto different processors in the multiprocessor architecture, and they can be made to concurrently execute and perform operation. Now the next thing that we have learned is it allows another thread to run when a thread makes a blocking system call. So this is also what we've understood. So if a user label thread makes a blocking system call, then the only associated kernel label thread will be blocked with no influence over the other kernel label threads. So other kernel label threads can perform its operation. So it supports multiple threads to execute in parallel over multiple processors. So here this is a typo error. So it is not microprocessors. It's multiprocessors. So multiple processors in a microprocessor system. So it supports multiple threads to execute in parallel on multiple processors belonging to a microprocessor. So this is the description of one-to-one model. Now examples, we have Windows NT, we have Windows Express, we have Windows 2000 operating system that supports one-to-one model. We have Linux, and we have Solaris 9 and later. So these are some of the notable examples of operating system that supports one-to-one model. Now we have understood that in case of one-to-one model, each user label thread has with it a kernel label thread, wherein even if a combination is blocked, it will not have influence over other combinations, and these combinations can be deployed onto multiple processors in the multiprocessor architecture. But one of the major limitations of one-to-one model, which is to be understood, that we can have only a restricted number of kernel label threads. We can have only restricted number of kernel level threads. So it has so one-to-one mapping has a very big limitation in that context. So since you have limited number of kernel level threads, you can have only limited number of user level threads that are initiated. Now let us discuss many-to-one model. So in contrast to many-to-one model and one-to-one model, in case of many-to-one model, we have mapping of multiple user level threads done to multiple kernel level threads with an imposition that the number of kernel level threads should be less than or equals to number of user level threads, just to overcome the lag of one-to-one model. So in case of many-to-many model, we have multiple user level threads being mapped to multiple kernel level threads, where the number of kernel level threads are less than or equals to the number of user level threads. So in case of many-to-one model, it multiplexes many user level threads onto equal or smaller number of kernel level threads. So in this model, developers can create as many user level threads as necessary, and the kernel and the corresponding kernel level threads can run in parallel on multiprocessor machine or multiprocessor architecture. So you see, this is one of the major advantage of many-to-many model over over one-to-one model and many-to-one model. So in contrast to one-to-one model, in case of many-to-many, we have many user level threads being mapped to many kernel level threads, but here the number of kernel level threads are restricted compared to that of one-to-one model, which creates kernel level thread for each user level thread. So in this model, developers can create as many user level threads as required, and the corresponding kernel level threads can run in parallel on multiprocessor machine. Now this model provides the best accuracy on concurrency, and when a thread performs a blocking system call, the kernel can schedule another thread for execution. So this is what is understood. So it provides the best accuracy because it optimally utilizes the space. And whenever a thread performs a blocking system call, the kernel can schedule another thread because the mapping allows you to map user level threads to kernel level threads that can be deployed onto the different processors belonging to the multiprocessor architecture. So creation of thread for every user level thread would create an overburden on the application, so as it can have restricted number of threads. So this is what we have learned in case of one-to-one model as well. So creating kernel level thread for every user level thread may not be possible because we can have only restricted number of threads in any of the operating kernel level threads or we can have restricted number of kernel level threads on any of the operating systems. So this is to be kept track of, or this is to be managed. So creation of threads for every user level thread would create an overburden on the application, so you can have only a restricted number of threads. So in today's class, what we've learned about is we have learned about what is a thread. So we have learned about let us span through it. So we have learned about what is a thread, right? What does a thread represent? What does threads belonging to a process share among them? What happens when we utilize thread, and whether a thread is a hardware approach or a software approach. And we have also learned about what threading facilitates. So it provides a very suitable foundation for parallel execution of application over a shared memory and multiprocessor architecture. Then we have made a distinction between the traditional process execution and process execution using threads with the help of a very simple schematic diagram, where we have shown that threads, different threads maintain their own status information with the help of individual system registers, program counter and stack, but they share the same data files and code, which makes them lightweight and less resource intensive. Then we created a distinction between processes and threads, where we have learned that process is rather heavyweight or resource intensive, whereas threads are lightweight and less resource intensive, because threads belonging to a process share the same common memory space. Then we have come through some of the advantages of threads, where we have learned that a thread reduces context switching time, it enhances concurrency, it enhances the overall system's performance, and it enhances the responsiveness of the system. It facilitates effective communication. It's more economical to create and manage threads, and threads utilizes the capabilities of multiprocessor architecture by deploying threads onto different processors in the multiprocessor architecture. Then we have learned about different types of threads, where we have learned user level threads and we have learned kernel level threads with its set of advantages and disadvantages. Then we moved on to a distinction between user level threads and kernel level threads. Then we moved on to multi-threading models, where we learned about why do we require multi-threading models. And we learned about different multi-threading models as well, where we learned about many-to-one model. We've learned about in detail with its set of advantages and disadvantages. Then we learned about one-to-one model with its advantages and disadvantages. And then we moved on to many-to-one model with its advantages and disadvantages. So this is all about threads and multi-threading models. So we'll learn about threads in a greater detail whenever we will be learning about different types of operating system. So thank you very much. Have a very nice day.